one derivative if you want to, factor none out of the denominator, just say it's equal to 1. Right? Okay? So what does that tell me? This series does the same thing as the series for 1 over n, right? So, do you know what 1 over n series does? Converges? How do you know that? How do you know that? So I heard it diverges now. How do you know what it does?
There's a box up there, and the half of the box, and we kept having the boxes. This denominator keeps getting bigger by 1. No, that was the different function. That'd be 1 over. Is that what this one would be? 1 over.
So this would be 1 plus half plus a third plus a fourth plus a fifth plus a sixth, right? Okay. So remember, don't compare it to something that you don't know what it does. Okay? But what does 1 over n do? And how do I justify what it does? Well, you find the limit as n goes to infinity. What does it go to? 0. Does that tell me anything?
No.
No. Does not tell me anything. It tells me that it has a chance to converge. Okay? Does not tell me that it converges, and that's huge. Like, you got to wrap your head around. I mean, it's a tough one. It's like, oh, I'm getting 0. Yeah, the terms are going to 0. Great. Right? It doesn't mean it sums to a finite number. Okay? Again, it's not that easy. Literally, then every single series I put up here pretty much will converge if that is the case. Because every one of these series, almost every series we will look at, the terms will go to 0 as n goes to infinity. Okay? Basically, every one we write out there. Almost all of them. There'll be a few exceptions, but those are exceptions. Okay? So, we're looking at 1 plus a half, plus a third, plus a fourth, plus a fifth, right? Yes? Okay? Trying to come up with what that looks like. And how can I justify whether that converges or diverges? We should know how to, we should probably know what the answer is. And 2, we should be able to use some stuff that we know to justify it.
Last unit, don't we know that if like the power is less than or equal to 1, it diverges?
Okay.
I don't remember what that was for.
And that was for what?
That would be,
When you what? Yeah, it wasn't a P series, right? It was for a what? What were we doing all last chapter? I know, so long ago. We were integrals. Yeah, we were improper integrals, right? We were integrating things. Yes? Right? We were finding if there was a finite area under the curve, right? Or an infinite, right? Yeah? Yes? Okay, so 1 over n is probably a lot like 1 over x, right? And summing up is kind of a lot like integrating, right? Because I'm pretty sure the integral symbol came from summation symbol, yes?
Yeah.
I believe we talked about that somewhere. Right? Yeah, right?
I think
Maybe?
so.
Right, I think so. Might have happened, right? Okay. So let's think about that. If you're integrating from 1 to infinity of 1 over x dx, right, that is finding the area under the curve from 1 to infinity, right? Yes? Okay? And what series are we trying to find? What's our series? Well, 1 over n plus 1 is what we're trying to find, right? You're comparing it to 1 over n. We'll come back to this in a second. So I'm comparing it to 1 over n, right? N equals 1 to infinity, right? Which is equal to
1 plus 1.
right? So, how can I put these two things together and make a connection?
The sum is greater than the integral. The sum is taking the rectangles, which will go above the integral curve.
Okay. So, if I start here, how high is this? 1, right? How do I make it equal 1? Make it a rectangle, right? That's 1 by 1, right? This is equal to 1. What's the height here? 1/2, right? Because that's when x is 2. So how big is this rectangle? Right? So this should sum to something larger than this, right? And what did this do? Diverged. So what's this going to do? Diverge. So what's this going to do? Diverge. Right? Yeah.
So if the sum of the symbol and the integral symbol mean exactly the same thing,
No.
okay.
Don't mean exactly the same thing, right? Summation was summing up an infinite number of rectangles, right? It's a continuous function. The series is not a continuous function, right? This is, rectangles that are 1 wide, or at least that's how we're interpreting them to be 1 wide. Those rectangles go to 0, right? Remember, we didn't get the integral symbol until we put a limit on here, and our change in x went to 0. Then I have an infinite number of rectangles, which is not what the series is doing. The series is summing up an infinite number of terms, but each one, our interpretation of them is each one is 1 wide. Right? I mean, that's kind of how we're interpreting to help us make this conclusion, right? Okay. All right, so the reality of it is we know this series diverges, right? And we know this series diverges kind of one of two ways, right? So yes, really, we want to make the connection to that it's simply a P series, right? That we can draw this conclusion, and that's a really easy one that we're going to, write up. Why does this series, why is a P series converge or diverge? Really based on an integral, right? Really based on an integral, okay? And so one way to do this problem is simply look at this, comparing it to 1 over n, right? Either through, can't do a direct comparison test to it, can we? No, because 1 over n diverges, but 1 over n is bigger than 1 over n plus 1, right? Yes. Because technically it's almost sort of a shift, right? That this 1/2 would be over here. Is that an accurate statement? So you'd have 1 compared to a half, and you'd have a half compared to a third, right? So every one of these series is bigger than the 1 over n plus 1 series. Yeah. Okay, so that wouldn't work. But the limit comparison test would work, right? Okay. So one way to do this is kind of through a combo of things, right? Is to look at a P series, right? So what we know, right? So our P series is the series from n equals 1 to infinity of 1 over n to the P, right? Right? And if P is greater than 1, the series converges. Right? If P is less than or equal to 1, series diverges. Okay? Plus. Okay. So the reality of this one, if I was, going to do it, I'm going to do a limit comparison test. All right, so if I was going to kind of write this up, all right, so we got this work, right? All right, and since the series 1 over n from n equals 1 to infinity converges, right, then the series n equals 1 to infinity of 1 over n plus 1 converges by, that's, yeah.
Okay, I was really confused.
Good job. Wait! Stop, what are you talking about? You're killing me. Diverges by
The
limit comparison test is really what I used, right?
Yeah.
Right. So how did I draw the how did I draw the conclusion about the series I was looking for? Right, by doing a limit comparison test with a series that I knew. All right. Now, this series, right, is what we call the harmonic series. Alright, so the series 1 over n from 1 to infinity is a special name. It's called the harmonic series. Right? It has a lot to do with musical notes and how the nodes are and stuff like that, and the fraction of the nodes when you cut and do some stuff with strings and whatever, there's some music stuff. Nobody's. I've had some people attempt to write up a good HLIA on it, and none of them have been done well enough for me to understand the connection of the harmonic to this. But there's something about the fraction and the ratio of where those notes are and stuff like that. Those of you that play instruments might know something about what I'm talking about.
So
Whatever.
if the series 1 over n is greater than 1 over n plus 1, why is it that we can say that 1 over n plus 1 diverges?
No, we did a limit comparison test. We didn't do a direct comparison test.
Okay.
We said we got 1. We said they do the same thing.
Okay.
So since 1 over n converges, then 1 over n plus 1 must converge.
Okay.
Right? We can't do a direct comparison test on this one, which is why we didn't do it, because it wouldn't be conclusive. All right? Now, with that being said, what's a different way I could have done this problem?
Just
You know, well,
Yeah, I could have tried the ratio test. So let's bring that up, right? I mean, it's a really good point, right? Ratio test is not a test to ever use when all you have is a polynomial, because you are going to get 1 every single time. Because again, all you're doing is replacing the n with n plus 1, okay? And so then literally you're going to have still n and an n, right? The plus 1 isn't going to change anything. It's still a linear, right? Or I don't care if this is n squared, right? If this is n squared plus 1, then my numerator is going to be n plus 1 squared, which is still going to be n squared, plus 2n plus 1, right? But when you factor out that n squared, the n squareds are going to cancel and everything is going to go to 1. Okay, so if all you have is simply a polynomial over a polynomial, okay, ratio test is not going to work. It is not a test I use when all I have is polynomials, okay? Polynomial good ideas are comparisons, right? Comparisons to this, right? That's a really good idea when I've got polynomials. I'm going to try to compare it to, a p-series. Okay, again, look at it. I've got an n squared up here. I've got an n cubed down there. Ooh, 1 over n, right? N squared over n cubed. I don't care what the other plus stuff is, right? It's going to act like n squared. The denominator is going to act like n cubed. Therefore, the whole fraction is going to kind of act like 1 over n, right? And I really like ratio or limit comparison tests for that, especially as you've got like n squared plus 2n plus 3 over n cubed, right? I don't know if that's bigger or smaller than 1 over n, right? Because I'm adding some stuff to the numerator, I'm adding and subtracting stuff to the denominator. Who the heck has time to attempt to figure out what that's doing, right? So limit comparison task is going to be much more, useful for that. Just compare it to 1 over n. Okay, get your answer from that, that way with it. Okay. All right, but we kind of talked about, we knew what this did because we did what with it? Compared to an integral, right? What can you do with this? Compared to an integral, all right, I can integrate this. Right?
Yep.
Just rewrite this as right? And antiderivative is natural log of x plus 1, right? Evaluated from 1 to b, say b better, right? Find the limit as b goes to infinity, right? You get natural log of b plus 1 minus the natural log of 2, right? And find the limit as b goes to infinity equals infinity, right? Right, natural log of b plus 1 as b goes to infinity is natural log of infinity, right? Which goes to infinity, right? Therefore, the integral diverges, right? Alright, so therefore the integral diverges. The integral of 1 over x plus 1 diverges, which means the series diverges by just the integral test.
Oh, nice.
Now, there's a couple of stipulations for the integral test, okay, in order to use it. There's some protocols, there's some criteria that's got to be true. So in order to use the integral test, basically you got to have a couple of different things happening. The function has to be a decreasing function, always has to be a decreasing function. Right? So the integral test, right, got to have a decreasing function. Right? So the terms have got to get smaller. I want to make sure I don't botch up what the 3 protocol is. Make sure I'm 100% right before I do this. So, how can I justify that this is decreasing? Well, I justify to make sure I'm 100% right. How would I show that 1 over x plus 1 is decreasing? How would I justify that?
The limit as x goes to infinity. Prove that the x's, as the x's grow towards infinity, it goes to 0. So
Take the derivative of it.
Maybe. Take the derivative and show that it's
Negative.
negative. Right? So a couple different ways. So yes, you can look at, the derivative would be a great way, especially since you're looking at an integral, right? Use your derivative, right? Use your calculus, right? If your derivative is negative, right, then your function's decreasing, right? Right. Okay, yeah, all right. So, 3 things it has to be. All right, so your function f of x has to be continuous, positive and decreasing. Okay? So it's got to be these three things, right? Which makes a ton of sense. Okay? First one, continuous, right? If your function is not continuous, at least on the interval that you're looking at, right? What does that mean I could have in my function? Discontinuity, right? Which specific one would be a big problem here? Yeah, the infinite, right? Right? Which is a huge issue that we had last chapter, right? That we looked at, right? And that was part of our improper integrals, right? So if we have an improper integral, right, we get the potential that we're going off to infinity somewhere. Yes? Okay? Which means the integral might diverge. Lots of times it does. Now you got that infinite area under the curve. Okay? But you got a series that is simply a bunch of rectangles. Right? That won't necessarily have that infinite value anywhere in them. Right? So you might find that your integral diverges, but that's not going to tell you what simply the sum of a bunch of numbers does. Right? So if your function is not continuous, then you can't use an integral test because, again, the conclusion of your integral test might not, what the integral does might not tell you, what the series does. Okay? It's got to be positive. Okay? So your terms always have to be positive, and it's got to be decreasing. Right? So again, we got that idea that we got a function that's doing this, right? Which is basically every function that we looked at last chapter, pretty much, that didn't have an infinite discontinuity, right? We looked at all these things that were coming down here and going to zero, right? And we're trying to figure out, was there an infinite or a finite area under the curve? It's the same idea with the series, right? And so basically, we've got this going on, right? So if, let's write the integral test up here. Add it to our list, right? So you got your integral test. So you got the series a sine, right? So you're going to look at if the integral from, this is n equals, a to infinity or something like that, right? The integral from a to infinity of f of x, right? dx, right? Or a of x, or however you want, right? Converges, then the series converges, right? Or you could say they do the same thing, right? If the integral diverges, the series diverges, right? But f of x has to be continuous, positive, and decreasing. Okay, so again, easiest way is f prime of x has to be less than 0. That's a good way to show that, right? So here, if I take the derivative of 1 over x plus 1, that's x plus 1 to the negative first, right? So that's negative 1 over x plus 1 squared, right? Which is always going to be negative, right? With the exception of negative 1, but that's not in the window that I'm, looking at, right? So this is always less than 0. Okay? It's always positive, right? Because x plus 1 is always greater than 0, right? As long as x is greater than negative 1, right? So therefore it's always positive, right? Justify that, very easily, right? And continuous, the only spot it's not continuous is at negative 1, right? Which again is not in the window that we're, looking at. Right? So again, those are kind of the big things. Again, come back to this for a second. We might get this, right? We've talked a decent amount. We're going to come back and spend a good chunk of time Monday, looking at alternating series and drawing some conclusions specifically about that, right? But this alternates, but